Traditional polyurethanes have gained widespread application due to their excellent mechanical properties, wear resistance, and processability. However, these materials are susceptible to cracking or fracturing under environmental stresses. In recent years, self-healing polyurethanes have gained significant attention as a critical research field owing to their key capabilities, such as repairing physical damage, restoring mechanical strength, structural adaptability, and cost-effective manufacturing. Self-healing materials are defined as those that possess the capacity to repair their own physical damage, in addition to restoring their physical properties. The extension of the service life of the material under consideration is conducive to reducing material waste, thereby increasing material sustainability. In recent decades, there has been a rapid development of self-healing composites of metals, ceramics, and polymers. According to a Fortune Business Insights report, the global self-healing materials market reached $5.58 billion in 2023, with polymer-based materials accounting for the largest share of the sector. In this context, polymers have emerged as a primary research focus for self-healing materials due to their distinctive characteristics, including superior mechanical properties, effective structural adaptability, and minimal fabrication cost. Waterborne polyurethanes, WWPU, have gained significant popularity in numerous fields due to their environmentally friendly characteristics. These materials possess a number of notable properties, including good abrasion resistance, flexibility, hardness, impact resistance, gloss, chemical resistance, low flammability, durability, high adhesive strength, ease of cleaning, low viscosity, and weathering resistance. WPUs are thus of significant industrial importance, with applications including coatings, adhesives, ink binders, glass fibers, paper sizing, synthetic leather, biomaterials, and waterproof textiles. Within the domain of packaging, WPU can be utilized in a variety of applications, including its role as a printing ink linker, as well as in the production of packaging film and coated film. In particular, polyurethane solutions have been shown to exhibit a certain degree of adhesion to substrates such as plastics, aluminum foils, and paper, among others. However, WPUs are easily damaged by external conditions, resulting in cracks or even fractures, which seriously affect the various properties of waterborne polyurethanes. In dry environments, rapid moisture evaporation can induce crack formation, while in humid conditions, cyclic moisture absorption, swelling, followed by drying shrinkage, leads to fatigue cracking. Furthermore, elevated temperatures accelerate both hydrolytic and oxidative degradation of polymer chains. Additionally, prolonged mechanical stress, or UV exposure, may cause chain breaking, resulting in crack initiation. In recent years, many researchers have explored self-healing WPU to achieve the purpose of prolonging the service life. And at the same time, self-healing WPU has ushered in many challenges. For example, the applicability of healing conditions and the conflict between healing and mechanical properties. The relatively low bond energy of disulfide bonds compared to other dynamic bonds shows the advantage of mild healing conditions. The development of self-healing WPU holds significant implications for traditional polyurethane coatings, particularly in intelligent research fields such as flexible sensors and electronic skins under room temperature self-healing properties. Incorporating self-healing properties into flexible electronic devices has been demonstrated as an effective strategy to mitigate mechanical damage during operation. This approach effectively extends the service life of materials and devices while reducing material waste, labor replacement costs, and life cycle expenses, thereby establishing a more sustainable pathway for low-carbon recycling. Self-healing polyurethane. Self-healing polyurethane is an intelligent polymeric material that achieves autonomous repair of damage, through dynamic covalent bonds or reversible non-covalent interactions, effectively restoring most of its original mechanical properties for 3 cycling times. In accordance with the principle of self-healing, the categories of self-healing can be divided into 2 distinct types: exogenous self-healing and intrinsic self-healing. External self-healing polyurethane material. The externally supported self-healing materials are achieved by pre-embedding microcontainers containing a healing agent and a corresponding catalyst in a matrix. In the event of material damage, the microcontainer that encapsulates the healing agent is ruptured beneath the surface of the material. This results in the release of the healing agent, which reaches the crack created by the damage and reacts with the catalyst within the matrix to repair the crack. This healing mechanism is ordinarily observed to occur at ambient temperature. It has been demonstrated that external conditions, such as light and heat, can accelerate the healing process and enhance the effectiveness of the material. The classification of externally supported self-healing materials is typically based on the structural characteristics of the microcontainer, including mainly 2 broad categories: microencapsulated self-healing materials and hollow fiber self-healing materials. Microencapsulated self-healing materials. This system achieves self-healing through ROMP, ring opening metathesis polymerization, which meets critical requirements including long shelf life, low monomer viscosity and volatility, and minimal shrinkage during polymerization. The ROMP reaction employs transition metal catalysts, Grubbs's catalyst, that exhibit high conversion activity while maintaining tolerance to various functional groups, oxygen and water. This reaction can polymerize dicyclopentadiene, DCPD, at room temperature within minutes, forming a tough, highly cross-linked polymer network. The research prospect of microencapsulated self-healing is promising, primarily due to its straightforward repair method and notably high repair efficiency. However, a compatibility issue has been identified between the microcapsules and the substrate, with the embedding of microcapsules having a detrimental effect on the substrate's original structure, consequently altering the material's mechanical properties. Furthermore, following the occurrence of microcapsule and polymerization, the microcapsule is rendered incapable of initiating the healing reaction. This phenomenon causes a limited number of healing times for the material and the inability to satisfy multiple healings in the same place. Hollow fiber-based self-healing materials. Microencapsulated self-healing materials present a significant disadvantage in that they can only undergo a single repair at their damaged site. This limitation has led to the proposal of the concept of hollow fiber self-healing. It has been established that it is analogous to the microcapsule self-healing mechanism. The triggering of both mechanisms occurs as a result of cracks in the microcontainer rupture, the overflow of the healing agent, and the catalyst within the matrix in contact with the catalyst. The catalyst is responsible for triggering the polymerization reaction, thereby achieving the healing of the material. The primary distinction between the hollow fiber type and the microcapsule type pertains to the configuration of the microcontainer. In the hollow fiber type, the healing agent is injected into the hollow fiber, which is prepared in advance. Subsequently, the hollow fiber is composited with the matrix post-treatment. The concept of hollow fiber-based self-healing materials was initially introduced by Dry's group, who proposed their storage within glass fiber tubes. The findings of the impact experiments demonstrated that the repair adhesive exhibited the capacity to migrate along the crack, in addition to facilitating the process of complete healing. Quantitative bending experiments demonstrated that this repair adhesive was also capable of hindering crack expansion. In accordance with this theory, researchers have constructed hollow tubes to meet specific requirements and employed various repair agents to facilitate healing. In short, The hollow fiber self-healing system is suitable for large-scale repairs and can be triggered multiple times, while the microcapsule self-healing system is ideal for rapid localized repair of micro-damage. The two can be combined to achieve multi-scale collaborative self-healing. Intrinsic self-polyurethane healing materials. Intrinsic healing is defined as self-healing that occurs as a result of the fracture reorganization of special chemical bonds contained within the material, thus negating the need for additional healing agents and corresponding catalysts. The classification of such special chemical bonds is typically performed into two categories: dynamic non-covalent bonds, which include metal ligand bonding, ionic bonding, hydrogen bonding, pi-pi stacking, and host-guest interactions. Dynamic covalent bonds, which encompass d-Alder bonding, acyl hydrazone bonding, disulfide bonding, diselenide bonding, and others. Intrinsic self-healing materials have attracted considerable attention due to the tunability of their material structure. Dynamic non-covalent bonds. Metal coordination bond. The metal ligand bond, the bonding energy of which falls between the van der Waals forces and traditional covalent bonds, is defined as a supramolecular force. This is formed by the complexation reaction between a metal cation, for example, copper, calcium, manganese, iron, magnesium, cobalt, and zinc ions, and an organic ligand. The complexation reaction is able to be stimulated by certain external conditions. Reversible fracture reorganization can occur due to the relatively good localization of the ligand bond, meaning it can be flexible in its choice of the appropriate ligand point. This has wide-ranging applications in self-healing materials. Hydrogen bond. In the presence of electrostatic forces, hydrogen atoms have been observed to be attracted to atoms or groups with higher electronegativity, such as nitrogen, oxygen, or fluorine atoms. Once the pairing occurs, a hydrogen bond is able to form between the two atoms. The bond strength of hydrogen bonds is lower in comparison to covalent bonds, resulting in a faster process of bond breakage and reorganization. The formation of hydrogen bonds can occur in a variety of ways, and they are categorized as either single or multiple hydrogen bonds. In general, the mechanical properties of polymers with single hydrogen bonds are suboptimal due to the weak physical cross-linking network composed of single hydrogen bonds. This is compensated for by multiple hydrogen bonds. Ionic bond. Ionic, or electrostatic, interactions are defined as physical bonds formed through electrostatic interactions between two ionic substances with opposite charges. These interactions are characterized as non-saturated and non-directional and result in a fracture reorganization response to changes in pH, thereby completing the self-healing behavior. The high response speed and high viscosity of polymer materials containing ionic bonds have led to their significant attention in the field of self-healing materials. Scientists successfully synthesized and characterized an alginate-based polyurethane elastomer exhibiting supramolecular interactions in the solid state. The material was constructed using ionic supramolecular motifs. These interactions confer simultaneous high rigidity and toughness to the elastomer, demonstrating broadly tailorable mechanical properties modulated by alginate content, reaching a tensile strength of 48 megapascals and Young's modulus of 93 megapascals. The elastomer displays rapid and exceptional self-healing capability, with healing efficiencies of 87.3% in the first cycle and 70.2% by the third healing cycle. Pi-pi stacking. Pi-pi stacking is a non-covalent bonding interaction force between aromatic rings, which is a relatively weak interaction force usually found in electron-rich and electron-deficient aromatic compounds. Pi-pi stacking is widely found in living organisms, such as nucleobase stacking and protein folding. A mild and solvent-free strategy combining classical chemical foaming with dynamic covalent chemistry to fabricate polyurethane Pu/hexagonal boron nitride HBN composites. Aromatic moieties in the Pu matrix derived from toluene diisocyanate T(D)I physically adsorb onto HBN surfaces through pi stacking interactions. Leveraging the material's reversible characteristics, the composite achieves a 95% healing efficiency. Although pi-pi stacking interactions endow self-healing polyurethane with highly efficient self-repair capabilities, such materials still suffer from inherent limitations, including low mechanical strength, insufficient modulus, and the requirement of external stimuli to trigger the healing process. Dynamic covalent bonding. Diels-Alder bond. Da bonds are formed through an addition reaction of an olefin with a conjugated olefin, which is a 4+2 cycloaddition reaction. The fabrication of self-healing materials based on Da bonds is achieved by means of temperature control, which results in the breakage and reorganization of Da, thereby imparting self-healing properties to the materials. Scientists introduced dynamic amine-Da bonds into the polymer backbone with a view to preparing a thermally driven, self-healing waterborne polyurethane film based on the Da fracture reorganization reaction. This also possesses recyclable properties. Following a self-healing process at 130 degrees Celsius for 30 minutes and subsequently at 65 degrees Celsius for 24 hours, the overall performance of the polyurethane film was restored. Reversible acyl hydrazone bond. The reaction of hydrazide with a carbonyl group, aldehyde or ketone, creates a reversible acyl hydrazone bond, which breaks and then reforms in response to aniline or acid stimulation. It can therefore be concluded that the addition of aniline or pH adjustment can lead to self-healing of materials containing reversible acyl hydrazone bonds. Scientists developed a novel polysaccharide-based self-repairing hydrogel. The hydrogel network exhibited dynamic acyl hydrazone and imine bonds, enabling dynamic fracture and reorganization to occur under mild conditions. The self-healing capability of hydrogel was substantiated through macroscopic self-healing tests, rheological recovery tests, and analogous methodologies. The hydrogel demonstrated a healing efficiency of up to 95%, a feat accomplished under conditions devoid of external stimulation. Imine bond. The imine bond is defined as a dynamic, reversible covalent bond formed by the condensation of an amino group with an aldehyde group, resulting in the formation of a carbon-nitrogen double bond. This bond exhibits dynamic properties associated with self-healing and reprocessability without the need for external stimuli. Consequently, materials based on reversible imine bonds have garnered significant interest from the scientific community. Scientists successfully prepared healing transparent PDMS elastomers based on imine bonding using amino-modified polydimethylsiloxane, PDMS, and 1,4-deformylbenzene, DFB, as the raw materials. The formation of imine bonds was demonstrated by infrared spectroscopy and Raman spectroscopy, and the reversible imine bonds could promote the self-healing of fracture surfaces without the stimulation of external conditions. The healing rate of the elastomer was found to be 42.6% after 5 minutes and 97% after 1 hour. The elastomer also demonstrated excellent recyclability and processability. Disulfide bond. Among the numerous dynamic covalent bonds, reversible reactions of disulfide bonds have garnered particular interest. Disulfide bonds are known to exhibit weak bond energies. Therefore, they are classified as dynamic covalent bonds. These bonds can undergo a reversible reaction known as fracture recombination, provided that the reaction occurs in the absence of external condition stimuli and at relatively low temperatures, 60 to 90 degrees Celsius. Consequently, disulfide bonds offer a significant advantage in the synthesis of dynamic polymers. Scientists utilized aromatic disulfides to prepare polydimethylsiloxane, PDMS. The completion of the self-healing process of this polymer was observed to require a mere 4 hours at ambient temperature. However, it was noted that the tensile properties of the polymer were found to be only 0.15 megapascals. While polyurethane materials incorporating disulfide bonds can demonstrate self-healing capabilities, this modification typically compromises their mechanical performance. Such trade-offs between self-healing ability and structural integrity have significantly constrained the practical applications of these materials. Furthermore, the commercial viability of these systems is limited by the high cost of aromatic disulfide monomers and the challenges associated with their industrial-scale synthesis. Self-healing polyurethane materials with different stimulus responses. Heat-initiated self-healing polyurethane materials. Thermally initiated self-healing materials are among the most extensively studied materials in this field. The majority of dynamic covalent and dynamic non-covalent bonds present within intrinsic self-healing materials are capable of being thermally initiated, with dynamic bond breaking and reorganization occurring under the influence of thermal conditions. The healing efficiency of thermally initiated materials is generally high, but there are some drawbacks, such as the effect of too high a healing temperature on the material's own structure, the tendency to age the material, and the inability to precisely locate the breakage. Photo-initiated self-healing polyurethane materials. Photo-initiated self-healing materials typically utilize light energy to induce or stimulate the reorganization of chemical bonds at the location of the breakage, thereby facilitating the self-healing of the damaged surface. Light energy is abundant, environmentally friendly, and safe. Thus, photo-initiated self-healing materials have attracted significant attention. The field of photo-induced self-healing can be broadly categorized into 3 distinct areas: photo-cross-linking reaction self-healing, photo-replacement reaction self-healing, and photothermal conversion self-healing. pH-initiated self-healing polyurethane materials. pH-induced self-healing materials are materials that have the capacity to promote self-healing by altering the acidity or alkalinity of the polymer. Scientists utilized whey acid to modify titosan and composite with 2,6-diaminopurin to prepare a self-healing supramolecular hydrogel, which exhibits the dual healing properties of thermal and pH healing. Electrically initiated self-healing materials. Electrically triggered self-healing materials refer to the self-healing effect achieved by using the Joule heat generated by an electric current to drive the dynamic bonding within the material to undergo reorganization. Scientists prepared a graphene thermoplastic polyurethane (GTPU) flexible conductive film using a blending method, which can stimulate the healing of the film by electrical and infrared light triggering. The excellent infrared absorption and energy conversion/transfer capabilities of graphene allow the temperature of the GTPU composite film to rapidly rise close to its softening point, thereby enabling self-healing of the composite film through wetting, diffusion, rearrangement, and cross-linking of TPU chains, followed by solidification. In the electrically stimulated healing process of the composite film, the temperature also increases due to electrical energy being converted into Joule heating, thus promoting the self-healing behavior of the composite film. Magnetically initiated self-healing polyurethane materials. Magnetically initiated materials have been shown to stimulate the occurrence of self-healing behavior by introducing ferromagnetic or superparamagnetic particles into the matrix and utilizing the magnetothermal effect generated by the magnetic field. Scientists prepared a magnetically initiated self-healing elastomer by incorporating Diels-Alder bonding and magnetite particles into polymers. The incorporation of Da bonding endows the polymer with self-healing properties, with the magnetite particles acting as the driving particles. A magnet was placed at the damaged section of the elastomer and simultaneously heated to enhance the material's fluidity. The magnetic field was utilized to induce electromagnetic effects, thereby stimulating the material's self-healing capabilities, thus facilitating the restoration of its integrity. Self-healing polyurethane elastomers are categorized into two types based on their healing mechanisms: intrinsic self-healing and extrinsic self-healing. Among these, intrinsic self-healing polyurethane can be achieved through the following approaches. Self-healing based on reversible non-covalent bonds, including metal-ligand coordination, ionic bonds, and hydrogen bonds, and self-healing based on covalent bonds, including Diels-Alder bonding, reversible acyl hydrazone bonds, imine bonds, and disulfide bonds. Depending on the stimulus applied, they can be classified as thermally induced, photoinduced, pH-induced, electrically induced, and magnetically induced self-healing. In the field of flexible electronics, self-healing polyurethanes have demonstrated immense potential as substrate materials for sensors, significantly enhancing the durability and stability of devices by endowing them with self-repair capabilities. The main trends of self-healing polyurethane will be functional diversification with medical electronic environmental integration. However, there are still challenges, including large-scale production with a facile process at low cost, balanced performance with suitable hardness and density, and a standardized testing system.